Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lecture we were discussing performance metrics, and we discussed specifically the oversampling scenario when we have a rare class of interest, very few records. So that was covered. We also talked about at the end of that particular lecture the two class scenario where some observation are difficult to be classified by our model, and we can have another third option, cannot say, and then that can be then manually inspected by experts and appropriately classified. So after that we come to our last leg of this particular module also, and this particular topic, performance metrics. So we will discuss the prediction performance. Till now whatever we have been talking about, right, was applicable to classification performance. Now we have come to our the last part, that is prediction performance. So when we talk about prediction performance, essentially it's about, we are going to focus on the continuous outcome variables. So generally we deal with continuous outcome variable. In the classification performance we had categorical outcome variable. So most of the things, they were dependent on the classes that it have, two classes scenario and extension into M class scenario and all those things that we have already discussed. Now in prediction performance the focus is now on continuous outcome variable. Now here again we need to understand few things that touch upon few things, specifically the classical statistical modeling and data mining modeling. Few things we can understand. Predictive accuracy, that is the metric that we generally use in prediction performance here in data mining modeling, and goodness of fit measures are generally used in statistical modeling. So main ideas behind this difference we have already discussed, but to be specific in this particular topic, performance metrics, goodness of fit, there in statistical modeling the main idea is to fit the data as closely as possible. We have one sample and we don't do any partitioning there. The same sample, generally primary data is collected in statistical modeling, and that the hypotheses that we have, they are tested, and on the same sample we build our model, and the same sample that then used is to find out the significance of that model. So that is generally done using goodness of fit measures, which typically measure how best the model is fitting the data. While when we talk about the data mining modeling, when we talk about the predictive analytics, we are focusing on how well we can predict the new observation, the future data. So there we focus more on predictive accuracy. So therefore in both these settings the scenario is different, and the measures that we use to assess the performance of the models are also different. Now if we like to discuss few examples for classical statistical modeling. So one would be goodness of fit measures that are generally used in regression modeling in a statistical setting. So these are two measures that we have shown here, R square and standard error estimate. So generally these two measures are used to understand how well the model is fitting the data in a statistical setting. So R square, as we have talked about this particular metric before as well in the supplementary lectures, that this particular metric measures the in a way captures the variability in the outcome variable. So how much variability in the outcome variable is actually being explained by the model, by the statistical model. So that in a way, in a sense, and variability when we talk about, it's about the information spread, the spread of data that is there. So essentially it boils down to the same thing, that how closely the model is fitting the data, how much variability in the outcome variable is being explained by the model or with the help of predictors information. Standard error estimate that we see in regression modeling, that is also in a way telling us how a particular the relationship between a particular predictor and outcome variable, how closely that is following, for example is being followed by the model. In this particular example, the regression model, right. So So, a standard error estimate would actually indicate that that fitting. Now, residual analysis is also performed to understand how well the data is, how well the model is fitting the data in a statistical setting. We do some analysis, we apply some visualization techniques as well while we analyze residuals, and we try to find out, we try to understand how closely the model is fitting the data and how it is being reflected in the residual series. Then when we come to predictive analytics, when we come to data mining modeling, right, so prediction error is one matrix. So prediction accuracy and prediction error on validation partition. So generally to performance, just like the classification performance that we have been talking about, that is the matrix, they are computed on validation partition. In the same fashion, even for prediction task, even to evaluate the prediction performance of a model, the matrix they are computed on validation partition. So whether it's prediction accuracy or prediction error, they are computed on validation partition, and that is where we compare the performance of different candidate models and then try to select the best model, the most useful model using these matrix. Now, as we talked about in the classification case, that naive rule provides us the benchmark, the baseline model, where we talked about if we if there are m classes, and naive rule would be for any new record assign it to the most prevalent class. So that we talked about, so that becomes the benchmark rule there in the classification. So the benchmark rule, it doesn't incorporate the predictors information, right? When we say that any new record can be assigned to the most prevalent class, then we are not incorporating, we are not analyzing the predictors information, and that is used as a benchmark, that is used as a baseline model. Similarly, in case of prediction, right, we use average value, we use average value of the outcome variable as the benchmark criterion. So the average value is actually that becomes the reference line, that becomes the baseline model, and those average value is actually used to compare the performance of the model. So all the candidate models that we might build on would be compared to this particular baseline model. Now, average value is in a way naive rule equivalent for the prediction task. Now, let us discuss a few metrics that are applicable in prediction task. So, generally this is the first one, prediction error. So, for any record I, we can always compute the error. So, for any record, once we build our model on training partition and we apply the model on different records that are there in the validation partition, or even for that matter in the training partition or in the test partition. So, for every record the model is going to give us a score, right. So, that is going to be the predicted value, and we will also have the information on the actual value of that particular record. So, the difference between actual value and predicted value, that is defined as the prediction error. So, prediction error for a particular record is defined as the actual value minus predicted value. It can be denoted in the mathematical terms as EI as yi minus yi bar. So, in this fashion we generally denote this. Now, there are some measures, predictive accuracy measures, which are popular, which are generally used to assess the performance of prediction models. So, we will discuss them one by one. First one is average error. So, if you look at the average error, as the name is suggesting, you can look at the formula that is written over there. You can see the residuals for all the records starting from, we have n records, so starting from 1 to n. So, when we say n, it could be any partition where we are trying to compute this particular metric, average error. So, it could be on training partition, it could be on validation partition, it could be on test partition, but the performance evaluation that is considered on the validation partition. So 1 to n for each observation starting from 1 to n, we have the that error value that we can compute using the formula that we just discussed before, prediction error, and we can summate these particular values and take an average. So we can divide it by n, this summation, and that will give us the average error. What does an average error indicate about the performance of the model? So on average, because these particular errors, they would be, if the actual value is bigger than the predicted value, the error is going to be the positive for that record. If the actual value is less than the predicted value, error will have a minus sign before its value. So therefore we will have positive and negative error values. So when we take an average of all the error values for all the observations that are there, on an average level we will get either plus or minus sign. So under prediction, over prediction, whether the model is under predicting or over predicting, that can be understood from the average error. Now let us discuss next metric. So next metric is mean absolute error, or MAE, sometimes also called mean absolute deviation, or MAD. You can also see the formula. So how this is being computed. So as we talked about that, a particular prediction error for a particular record, it could be positive or negative. So because as the name suggests, because we are we want to compute absolute error. So for each error for each record, we take an absolute value of it, and then again we take the average. So that is how we get the mean absolute error. So this particular metric gives us the magnitude of error. So on an average level, we get the magnitude of error which we are getting from that particular model. So how much magnitude of error, in a way, per observation is being is coming from the model. So that we can get using this particular metric. So let us move to next matrix. So next matrix is mean absolute percentage error, or MAPE. Now as the name is suggesting, so still we are trying to compute the absolute values, but now we are interested in percentage values rather than the actual values. So to compute the percentage value, you would see that the whole formula, before the formula we have this 100%, it is multiplied by 100%, so that the percentage value can be computed. Now if we look at the actual expression, the error value is being divided by the actual value, so that we get the the difference, and then absolute has been taken. So it could be on either side, positive or negative side. So we take that difference, that quantum that is there, using error values divided by the actual value, and we take the absolute value of it, and then we take the average for including all the observations, and then the percentage value. So what this particular metric tells us about the model, that as you can see in the slide, that on an average level, what is the percentage deviation from actual value that is being given by the model. So what is the percentage? So how the values or the kind of deviation, that is the predicted values, what percentage point they are deviating from the actual values for that particular model. So that thing we can understand using this particular metric. Now let us move to our next metric. So this next metric is the more important one among the ones we have discussed. Region will understand. So this one is root mean squared error, also called rmse. If we look at the formula for computing this particular measure is square root, and then we are taking the average value of the squared errors. We are summating all the squared errors and taking average of it, and then taking square root of it. So you can see when we take a square of a particular error, so the sign that we get in a error, in the prediction error, plus or minus, positive or negative sign, that is taken care of. Now we have a squared values. Now all these values are summed up and then we divide it by n, so that's we get the average. So we get the square, mean is squared error. Now again we take the square root. Once we take the square root, again we go back to the same scale. So this particular scale, once we take the square root, it is in the same scale as the scale of prediction error, that is computed on the outcome variable. So rmse is very similar to a standard error estimate computed on validation partition. So we talked about the standard error estimate in the context of statistical modeling, right? We talked about R square and standard error estimate. If we want to have one metric which is quite in the predictive analytics which could be used and which is quite close to a standard error of estimate that we get there, this is the rmse is the matrix. So this is something that we get for the model. So from this we can understand that on an average level with respect to the outcome variable, what is the error that is there. Now this is also another advantage with this root mean squared error is that measured in the same unit as the outcome variable. So because of these reasons, rmse is one of the popular metrics to evaluate the performance of a model. So whenever we would be comparing performance of different candidate models, rmse is the one value on which we will rely to evaluate the performance, to compare the performance. Reason being main reason being that same unit as the outcome variable, right, and quite similar to the standard error estimate that we have in a statistical setting. So for that purpose we do use that metric. Now the another metric that we might be interested in total sum of squared errors, sometimes called total SSE or simply SSE as well. So how it is computed? Simply all the errors is square values of those errors and then summation for all the observations. So that computes us for the total SSE. So this, what does this particular metric indicate? So this particular metric indicates us the gives us the total that overall sense of error that is being given by the model. So if we are comparing two models, then we can look at the SSE value, what was the SSE value for model 1, model 2, model 3 and onwards, and this particular value will also give us the sense that which model is performing better. Though the scale of these errors would be different, but comparison is still feasible. So this is to give the overall sense of the error for a particular model. Now these particular matrix measures that we have talked about for prediction task. So where we can use them? So we can use them to compare the candidate models as we have been discussing. We can also assess the degree of prediction accuracy that is there. Now what is the problem with these matrix? There are the matrix can always be used, can there be a few issues? So outlier related issues could also be there. For example, all the matrix, all the formulas that we talked about, they generally consider all the observations, and when we they consider all the observation, they include all the error values, all the prediction error values, irrespective of whether it is lying within the majority of the values or whether it is an outlier value. So that might complicate the assessment of models. So how do we overcome such a situation? How do we overcome outlier influence in our measures that we have discussed? So we can we can use some of the median based measures, and we can compare them with the mean based measures. So from that comparison, just like what we do in when we check for normal distribution and whether it is right skewed or left skewed, we look at the median and mean values. If mean value is higher than median, then probably it is right skewed, and if the reverse is true, then it is left skewed. In the same fashion, we can compare the median based measures and the mean based measure and from there we can get a sense whether outliers, the kind of influence that outlier have. Another way would be to apply visualization techniques. For example, we can use histogram or box plot of residuals. So we can generate histogram and box plot of residuals, and from there we can the same kind of thing we can observe there, what we do for normal distribution when we check for skewness. The similar kind of observation we can make and then check for the outlier influence. Now another point that we need to understand at this point is that when we build a model in a statistical setting, and when we build a model in a data mining setting, and in data mining setting we are going for the higher predictive accuracy, and when we talk about a statistical setting we are going for the best fit of data. So the model that we get in these two different settings, they may or may not be same. So the model that we get when we build a model in data mining setting and using the metrics following high predictive accuracy, it might be different from the model that we get when we build a model in a statistical setting while we are looking for best fit of data. Now can there be visualization techniques which could be used to evaluate the performance of prediction models? So lift curve is one which can be used. Now lift curve, the exposure that we have till now, we have been using lift curve quite often. So it is going to be relevant only when records with highest predicted values are sought. So as we have seen before, that generally in lift curve we compute some values and then we take accumulated numbers, and then those accumulated values are then plotted against the number of cases there, and then we try to assess how much lift we get in comparison to the baseline model. So in prediction tasks, if we have a situation wherein for example sedan car data set that we have been using, if we take an example of sedan car, and there is a company and they have multiple channels to sell their sedan cars, right? So different channels might give them different kinds of revenues, right? So and especially the data set, if it is for example if it is for used cars, right, so therefore it becomes difficult to assess the price. New cars, this is fixed from the manufacturer side. So but when we talk about used cars, the prices might vary, and therefore different channels, how different channels can be used by the firm to sell those cars. So lift curve can be useful in that sense. For example, a particular firm might have few of its own channels, and few it might also use some of the channels operated by third parties. So the firm might look to retain look to sell the highly priced cars through its own channel, so that it can make more revenues and therefore more profit using its own channel. And some of the low value used cars, they might go with the third party channels. So that can be done using lift curve. So we'll do an exercise in R to see how this is how this can be done. So this is this small data set that we have. You can see we have already a column called value, serial number is there, then value is there. This value of are the can be considered for the cars, sedan cars, premium cars. So they are ranging from 9 lakhs to 50 lakhs, 8 lakhs to 50 lakhs. So random functions were used to generate these values, and then these values were then later on sorted in the decreasing order. So as you can see, once they were sorted, then the cumulative scores were also computed, as we have been doing before as well. So you can see the cumulative scores have been computed. So this is how you can generate the data. Now what we are interested in, the for example higher value cars. So which ones are the which first 10 cases are the having the highest value, right. So we would like to identify those high value cases, right. So let's open RStudio. Let's load this library XLSX. Now the data set that we have just seen, it's in this particular file, cutoff data. Let's import this particular data set. Let's remove the NA columns, and first 6 observations. So this we have already seen these observations, cumulative value. So we would like to plot these cumulative value with respect to the serial numbers that are there. So let's look at the range that is there. So the range is between 49 to 544. So this is the cumulative value range that we have. Serial numbers, I think we have just 20 records, so range is going to be 1 to 20. So you can see the plot the way we have been doing before as well. The first variable, first argument is going to be plotted on x-axis, that is serial number. Then the y argument, second argument, cumulative value, that is going to be plotted on y, and the type of the curve is line. Then labeling for x-axis and y-axis, cumulative value for y-axis is given. Limits have been appropriately specified. As you can see, range we have already computed at 0 to 25, and then we have this 40 to 550, which is covering the entire range that we saw. So let's execute this line of code, and so this is the plot that we get. So as you can see, this is smooth plot, lift curve has been created. Now let's also draw the reference line. So reference line would be connecting the initial point with the last point that we have. Let's draw this. So this is the reference line. So this lift line that we have, so there is good enough separation between the lift curve and the reference line. So therefore model is useful and giving us some effectiveness in terms of identifying those high value cars, right. So high value used cars, sedan cars, the model is giving us some usefulness, and we can have those cars and sell those cars using our own channels, if right. And the other cars, the low value cars, we can probably push them through third party channels. So let's also create the legend. You would see the cumulative value is sorted by predicted value from this left curve and then the reference line. Now the information that we have just depicted using lift curve can also be done using the decile chart, like we had done before for classification tasks. So let's create a decile chart for prediction tasks. So in this case also, because we would like to have 10 deciles, and each decile representing 10% of the cases, then 20%, 30%, and so on. So we would like to create this variable which will have the information on the for every decile, the number of observation that would be there. So you can see sequence, and the length is of this particular variable, which will give us the total number of observation, and that would be appropriately distributed for each decile. You would see that 2, 4, 6, 8, 10, 12 in this fashion will have the distribution. Now a few other variables, decile, that is where we would be computing the decile values that would be plotted using bar chart later on. Decile mean, so this we want to compute. So let's initialize this value as null. Now global mean in this case would be, you would remember how we computed the global mean for the classification task. Now here we just need to compute the average of this particular column, and we'll get the global mean. So global mean comes out to be 27.2 lakhs. Now let's initialize these counters. Now we are going to run this particular for loop starting in decile cases. For all the decile, 10 deciles are there. So for each deciles, this loop is going to be run, and we would be computing in every loop decile mean, which is right for every decile. This is actually nothing but the cumulative value that we have up to that decile, and divided by this particular number of that decile, right. So that will give us the decile mean, and then we can divide the decile mean by global mean and then that will be used as our decile value. So let's execute this particular loop, and we'll have all the decile values here. You can see all the desired values starting from 1.76 in the decreasing order, they are going to be there. So let's look at the range. The range is from 1 to 1.76, and now we are going to generate this bar plot, which would be creating this decile chart. So decile 1, these values, decile values that we have just computed. Y limit is representing the range, 0 to 2 is going to cover that. Deciles label of the x-axis, then the label of y-axis, decile mean divided by global mean, and the arguments appropriately specified for each decile. So let's compute. So this is the plot that we generate. So this is the decile chart that we have. So as you can see, decile 1 representing 10% of the cases. So the value as we have computed, it's 1.76. So it will give us the lift of 1.76 in comparison to the baseline model, in comparison to the random selection scenario. So these probably these 10% cases, so we would be interested in selling these used cars, these premium sedan cars, using our own channels, because we might generate more revenue, more sales through this. Similarly, for decile 2 also we get a good enough lift value, right? This is also more than 1.5, it is actually 1.7. So in this fashion we can find out the optimal we can take the appropriate decisions till the appropriate lift value. So lift value of more than 1 would be useful for us. So in this fashion we can find out the number of cars that we would like to sell through our own channels. So thank you. So we'll stop here. So that concludes this particular module, and in the next lecture we'll start the next module, that is on supervised learning methods, and the very first technique that we are going to start on is the multiple linear regression. Thank you.